start. Um, I'll do a recap of gravitational fields from the beginning. So if you have missed the last class or at least didn't understand this part, I'll start from scratch again. Okay. So we started a new chapter, gravitational fields, and I just give you a brief introduction to it. আজকে আরো details এ করবো. Okay. Right. So our syllabus is divided into three parts. Let me explain what are the things we'll be going through. So right now I'll be starting this one. It's called just the gravitational field. So what's the gravitational field and how do you represent it? So that's the first part. That will probably be done by today. Then comes the core of our chapter, which is the gravitational force. And there are two parts to it. One is the force and the other one is the field strength. So these two are the core part of our chapter. And then you have potential. This is not a very big chapter or a very big topic, but it is complicated. Okay, so a last students usually struggle with because the concept is a little difficult to grasp. Anyways, we'll try. So let's start with gravitational field. So what's a gravitational field? Or what's a field in general? So field হচ্ছে, if you ever come across this word in physics, it has one meaning only, field. So field হচ্ছে a region in which force is exerted. A region in which force is exerted. So if you have a field, it means it's a region where force will be experienced, right? Exerted or experienced দুইটাই হবে. So the question is, what are the types of fields out there? So in physics, there are famously three different fields that we study. Now, in the syllabus এর মধ্যে যেগুলা আছে ওগুলো বলি. So we have gravitational field. That's the one we'll be studying right now. Gravitational field. Then there is another field we'll be studying very soon. It's called the electric field, which you have some idea about from your O-levels. And then this one also you have some idea from your O-levels, which is called the magnetic field. So these are the three different fields that we have in our A2, the gravitational, electric, and magnetic. Now, I have a couple of questions for you guys, because since you have actually done this before, let's start it that way. So can you tell me, the gravitational field is a region, right? It's a region in which what experiences force? So what do you need to be so that you can feel the force in a gravitational field? Right, very good. Mass. So gravitational field is a region in which masses experience force. Mane, if you have mass, you will experience force. And that's what we do, right? As humans, we have mass, so therefore we can experience the force that gravity exerts, right? Now, for you to be experiencing force in an electric field, what do you need to have? Right, very good. Charge. So if you have charge, you will experience a force in an electric field. Now, we typically are neutral in terms of our charge, so therefore we don't really experience any force in an electric field. And lastly, you have your magnetic field. So if you want to experience a force in a magnetic field, what do you need to be? It's tricky. I don't really expect students to know this, but Shigbo, is there anyone who knows? For you to experience magnetic field, right? What do you need to be? Acha. So this one is a little strange. It is actually charge. So you need to have charge to experience force in a magnetic field. However, there's a catch. Not any charge. It's moving charges. So any moving charge will experience force in a magnetic field. And eventually আমরা শিখবো যে যত কিছু দেখে আসছি আমরা magnetism-এ, there are actually involvement of moving charges. So if you remember the Fleming's left-hand rule, right? There's current flowing through it. If you understand how dipoles exert forces, right? They're actually electrons that are spinning. So yeah, these are the three fields that we have. In fact, our syllabus is designed around three fields here. So you have the gravitational field, যেটা mass experience করে. You have the electric field, যেটা charge experience করে, and you have the magnetic field, যেটা moving charge experience করে. So এগুলা সবগুলো আমাদেরকে শিখতে হবে to quite a detail. মানে we will learn all the equations and everything about it. So we'll start with the gravitational field আজকে. Right. So is there a derivative of how magnetic field strength is directly proportional to current flowing? Magnetic field strength directly proportional to current flowing. There's actually a formula for it. We don't have it anymore. B equals to mu I divided by 2 pi r. This is no more in our syllabus anymore. But yeah, there is an equation that helps you understand the strength of magnetic field based on how much current is actually passing through. It used to be there till 2011, I think, but after 2011, they got rid of it. Right. So let's see. Right, gravitational field. Now, for simplicity purpose, uh, our A2 gravitational field has some assumptions that we make. Okay, so ওটা আগে দেখাই নি. So gravitational field for A2, but just generally speaking. Okay, so the first thing that you need to know is that we will only be dealing with masses in an isolated space. Masses in an isolated space. What does it mean? So this will be a lifesaver for you when it comes to calculations. Why? We will only deal with scenarios where our mass is in isolated space. It essentially means there's nothing around it. It's just your mass out there, which is highly unlikely in real life. So even if you go to the deepest, parts of the universe, right? The most empty parts of our universe, gravity is not zero there. The force of gravitation is not zero. You are constantly being attracted through uh, forces that are from other masses very far away. And then the reason behind that is gravitational force and field is actually infinite in nature. Its range is infinite. So wherever you go in space, you will experience the impacts of gravity. And and the thing is that that's the reason why the universe came into existence the way we know. The formation of stars and galaxies is because gravity eventually brought all the particles together. And it was only successful in bringing all the particles together because its reach is infinite. It could bring particles from the different parts of the universe all together in one place. And in that process of coming to that one place, it led to the formation of stars. We'll learn that. Actually, we had it in all levels, so A2 theta naive. Right, so that's the first assumption that you have. আরেকটা হচ্ছে এটা assumption না, but it's just what the feature of a gravitational field. Gravitational field is only attractive. So there is no repulsive gravitational force out there in the universe. So only attraction can take place through gravity. Okay, so that's the other assumption that we have, not assumption, like a feature. And the last one that you have is masses are considered to be, this is also very helpful, point masses. What does that mean? It means we assume that the masses don't have any shape or size. And that is very handy. I'll show you why. So when we deal with gravitational forces, we have like rocks in space. Let's say this is a asteroid, and this is another piece of asteroid through space, right? And it's floating through space. According to the law of gravitation, which we'll learn very soon, these two rocks that you see here, they will attract each other. So gravitational force is attractive in nature, and it's between any two masses out there. So any two mass you can imagine is actually providing gravitational force on each other. So you are currently applying gravitational force on the chair, the table around you. You are applying gravitational force on the fan. The chair is applying gravitational force on the things around it. So basically, gravitational force is between any mass out there, right? And it's only attractive in nature. But the thing is, most of the forces that are out there are so negligible that it's not even measurable. So gravitational field এটাকে জাস্ট এক্সট্রা পয়েন্ট দিয়ে রাখতেছি জানার জন্য। The weakest field in the universe. Weakest field in the universe. এর চেয়ে উইক কোনো ফিল্ড হয় না। So think of any other field out there, they're much stronger compared to gravitational field. And something the size of the Earth, okay, 6.02 into 10 to the power 24 kilograms. That's the mass of the Earth. Something this big, right, can only apply 10 Newton on a 1 kg mass out there, like 9.81 Newton. So that's the force you apply when you hit something with your hand. Just the gently কোনো কিছুকে tap করো, the amount of force you apply is the force that the Earth applies. The entirety of Earth applies on a 1 kg mass. So it's very weak. It's the weakest field out there. Okay. So yeah, the two masses that you see here will attract each other. So এটাকে attract করবে, and this is attraction, obviously. And this is M1 and M2. So we model this as 2 points attracting each other. And the points that we will consider here are their center of masses. So when you look at these two masses, right, the points are the center of masses that are attracting each other. Okay. So this is the center of mass here. This is the center of mass there. This is basically the attraction that's taking place. Right. So we'll call it M1 and M2. আমরা কি করবো, আমরা ignore করবো এটা shape and size, which makes our life very like easy in A2. Obviously, once you go to higher levels like university and you take physics, right, you wouldn't be assuming that, and you'll take the actual shape into account. Is the strongest field electric field? No, no. So there's this force field which we don't really study in our A levels. It's the strong nuclear force and the effects of it. It's found within the nucleus of an atom, and that is the strongest force in the universe. So its field is the strongest, and it only acts within the nucleus of an atom in the smallest gaps possible out there. So the separation has to be extremely small for that force to materialize. So you can only see its impact and effect when it comes to the sizes that are similar to the nucleus of an atom. Right. So gravitational field হচ্ছে masses are isolated in space. It's only attractive in nature. The masses are considered to be point masses, and there's attraction between two masses out there. And gravitational field হচ্ছে a region in which a mass experiences force. Okay. So to give you a simple example, this is the Earth, and the region around the Earth, right, is where you have a mass. So like a random mass রাখলা এখানে, and you'll notice this mass experience a force, the force that we call the force of gravity, right? So this force that's been experienced here is because this mass is within the Earth's what field? Gravitational field. Okay, so the Earth has a gravitational field around it, and this mass is within that field. So this mass experiences a gravitational force from the Earth. Now, I have some questions for you. These are things that we talked about in O levels. O levels এ জিনিসটা কি ছিল, অত ইম্পর্টেন্স দেওয়া হতো না, বাট A levels এসে আবার কনসিডার করা হয়, তোমরা তো জানো। তার জন্য I just want to be clear about it. Do you know that the Earth is actually applying a force on this mass here, and this force has a label? Can anyone tell me what should the label of this force be? This force that's exerted by the Earth on the mass, right? What would you call this force? Centripetal? No, no, centripetal হবে না তো, এটা তো just a mass falling. It's not going in a circle. Yeah, so you'd call this gravitational force, right? Typically we just call it weight, but the right way of saying this is, the right way of phrasing this is gravitational force of Earth. এসে ছিল এটা on object rock. Okay, that's a rock. On rock. Now there's something called Newton's third law of air, And according to that, every force must have a pair force out there. Can you recognize what was the pair force of this? ওইখান থেকে নিউটন অ্যাকচুয়ালি ডিসকভার করেছে গ্র্যাভিটি। I'll tell you the story how Newton actually came up with the story of the apple to make people understand. Yes, very good. So the pair force is going to be this one, right? Equal and opposite. And the pair force is going to be gravitational force of rock on Earth. Gravitational force of rock on Earth. মনে আছে তোমাদের এটা? So there are a few things that you needed to remember. The two forces that you see here, they're of what magnitude? Equal and opposite magnitude, right? And direction opposite. So you know all the requirements of third law pair, equal magnitude, same line of action, same duration, the approach is same type of force, and different কি they were in opposite direction and they were acting on different objects, right? This is where Newton understood this. Okay, when Newton understood that there's a third law pair, and that's when he realized the existence of gravity. So what's that apple story out there that people tell, like, Newton's the apple fell on his head, right? It didn't, but he used it as an example. So basically, the idea was that there's a tree, and he explained this way. আচ্ছা আমি বুঝাই জিনিসটা তাহলে তোমাদের একটু ইজিয়ার হবে বুঝতে যে why did it take so long for gravity to be understood? মানে what was holding us back? You have your apple here, and momentum, right? If something has momentum, the total momentum must be conserved, right? So he said that if there's an apple hanging from the tree, and what happens is that the apple falls, the apple is moving downwards, right? So as the apple falls, it gains momentum. Do you agree? Apple it's gaining momentum here, right? So let's call it positive P. But the apple was stationary initially. So the sum of the momentum, right? Sum of momentum before this event took place, initial momentum must have been what? Zero. Because the apple was stationary. And suddenly the apple is falling. So it means the apple now has a positive momentum. And momentum can't be created or destroyed. It's always conserved, right? So you just can't create momentum out of nowhere. So what's happening here is suddenly you have momentum of plus p, but the system must have a momentum of how much? Zero. So that's when Newton was like wondering, wait a second, you can't create momentum, and he has proven this very well using ideas of mechanics and calculus. But while looking at an apple falling, he started wondering, it has a positive momentum, but the total system must be zero. So who has the negative momentum? Somebody must have to lose momentum for the apple to gain momentum. Because on a total to zero থাকতে হবে. And that's when that moment clicked for him. He realized, wait a second, there must be something exerted by the earth on the apple in the opposite direction. I'll explain. So his hypothesis was, as the apple fell downwards, the earth moved upwards, and the earth moved upwards with what momentum? Minus p. And if you take the total momentum together, it becomes zero. And momentum is rate of change of momentum is force, right? So from there he realized that there must be a force acting downwards, which he called force of gravity, and there must be a force acting upwards, which is also the force of gravity. They're equal and opposite. That's where he came with the idea of gravitational force, that the earth is applying a force on the apple, and then the apple is also applying equal and opposite force on the earth. That was a missing piece of the puzzle. People never realized that the apple is also pulling the earth. People always thought the earth is pulling the apple, but then they couldn't figure out how and why. But the moment they realized that the apple is also pulling the earth, that's the dawn of gravitational forces and fields. Okay, so that's the story that he used. He basically used very basic Newton's laws to explain the origin of gravity. and eventually he went on to discover more things about that force. Okay, so yeah, that's all about the origin of the force in the field. তোমাদের কোনো কোয়েশ্চেন থেকে আমাকে বলতে পারো. So what are the key takeaways from here? Number one is that gravitational field is a region in which a mass experiences force. Secondly is that for our syllabus, we'll assume that the masses are isolated in space, like far away from everything, that the force is only attractive in nature, as in there's no repulsion out there. This is not even an assumption. This is how what a fact. Gravitational forces are not repulsive, and masses are considered to be point masses for calculation purpose. So even if you have like rocks like this, right, that are being attracted in space, we'll assume their center of masses to be attracted. What shape and size they have is irrelevant for us. Okay, so yeah, this is the gravitational field, and এখন আমরা start করবো হচ্ছে the idea of field lines, like how to draw the field. So I started that last class, but আরেকবার বুঝাই নি তোমাদেরকে. So how do you represent the field? So let me explain why representation of field is very important. So we know that the Earth is here, and we know that around the Earth there's a region where gravity exerts its influence, right? So question is, how far is it? The place where the Earth is exerting force, right? How far is it? I already mentioned this earlier, but can you remind me? Earth gravitational field range কত দূর? What's the range of the Earth's gravitational field? Yes, it's infinite. It is actually infinite. And this is, I know it may sound strange, but it is what it is, that the distant galaxies that you see out there, right? Andromeda, it's not a distant galaxy, it's actually the closest galaxy, but stars in Andromeda are pulling on you right now. They're applying gravitational force on you right now. But the Earth's force is stronger, so you're sticking to the Earth. Let's say the Earth just disappears hypothetically right now. Where do you think you'll move? Yes, very good. To the sun, because the sun is the next strongest thing out there, right? Um, Technically speaking, if the Earth disappeared right now and the moon remained, the moon could be a place you might go. Actually, it depends on at what position you are compared to the moon and the sun. But yeah, you'll probably go to the sun. What if the sun disappears? Where will you go? Let's say the sun just disappeared and then we are on Earth, right? Where will we go? Who will have a stronger force on us? Any guesses? So if the sun disappears, right? No, no, no. Earth to আসি আমরা. Uh, আচ্ছা, let's make it simple. Earth চলে গেছে, moon চলে গেছে, sun চলে গেছে. You're floating in space. Will you just float in space or will you go somewhere? Yeah, you'll go to the nearest star, because the nearest star, Proxima Centauri A or B, ওগুলো হচ্ছে nearest star. ওগুলার ফোর্স তোমার উপরে তখন সবচেয়ে বেশি থাকবে. ওরা ডিসঅ্যাপিয়ার হয়ে গেলে you most likely end up at the center of our Milky Way. If the Milky Way disappears, you'll end up at the other galaxy out there. My point is, you're always under the influence of something's gravity. When there's something always influencing it's exerting its gravitational force on you, regardless where you are in space. Okay, so the force of gravity and the field is actually infinite. But here's the catch, though: it's not equally strong everywhere. So the further you start to go, right, it starts to get weaker. So how do we represent that in a diagrammatic way? So আমি একটা way চেষ্টা করলাম, এই যে I don't know তোমাদের স্ক্রিনে বোঝা যায় নাকি, but I'm using shades to show different strength. So if you look at the diagram that I tried to draw here, you'll find that um, the center is the strongest, right? আমি একটা জিনিস দেখাই তোমাদেরকে কেন ফিল লাইন্স ইউজ করা হয়. So yeah, এই সেন্টারটা সবচেয়ে strong. বোঝা যাচ্ছে the color gradient here, and you start to go and the color shifts, right? So this is one way of explaining strength, right? But not everyone will have a colored page. Not everyone will have colors to understand, and also colors are not universal. So this way of representing a diagram might work for you and I if we discuss and draw it. But a third party person, like somebody who hasn't seen the diagram before and doesn't know the color meaning, wouldn't know this, right? So to avoid complications of these type, we eventually came up with a convention of representing field. And you know that we use lines. So lines use kora hoy with arrows, and they represent your field. And the way you can draw your lines can represent the strength and whatnot. So let's just quickly discuss about fields before we draw the gravitational field. Fields are represented by lines with arrows. Okay, so that's first thing. Now, when your lines are parallel to each other like this, right? এরকম দেখতে. This is considered to be a what field? Can anyone tell me? We had this in O levels. What would you represent or call this field as? Yes, very good. It's called a uniform field. Uniform field. Okay. So uniform কেন? The line spacing is equal because equal spacing. Okay. So because equal spacing, that's why it's uniform. So the spacing is important. Equal spacing. Now, if I take this field and draw another field here, can you tell me what's the definition of the field that I've drawn below? Yeah, it's all still a uniform field. Very good. It's also a uniform field. But compared to the previous one, what is it? Right. It's a weaker uniform field. Weaker field compared to the above. Cannot weaker because concentration of lines are few. So lines are not that concentrated. So yeah, fielder জিনিস হচ্ছে you need to have arrows. The concentration of line represents strength, and weaker field compared to above. So this is a weaker field out there. And the other thing that you need to know is that whenever we draw field lines, especially for gravitational field and electric field, the field lines must leave the surface perpendicularly. Okay, this is a requirement. So they leave a surface at 90 degree. 90 degree. So any field line that leaves a surface must be 90 degree. Can you tell me what's the consequence of that in terms of where they come from within the circle? If they're 90 degree to the surface, right? What does that mean in terms of where they originate from? No idea. In the circle, where do they all originate from? If they have to leave the circle at 90 degree. Yes, very good. So we talked about this in circular motion, that if you draw lines that are perpendicular to the surface of a circle, they can be stretched and they will always have to meet at the what of the circle? The center of the circle. Okay, so that means the field lines originate from the center like that. Right. So, anyways, these are a few things that you need to know. So, what we do is we take these ideas and we draw our field here. And once you draw a field here, you'll start to realize that by using lines, you can actually represent the field very easily, where everyone will understand what's happening. So, what you have to do is you need to draw the lines, pass into the center, and leaving the circle at the surface at 90 degree. Okay. So draw coordinate to the so this is how the field lines are drawn. Now for gravitational field, because it's only attractive in nature, we put the arrows pointing inwards. They don't ask this question, but they might sometimes, that why are the arrows pointing inwards? And the answer to that is the arrows represent the direction in which the mass moves. So এখানে যদি কোনো mass রাখা হয় in this field, right, where will it move? Towards the center. So I'll add that later on, but right now this is what the field looks like, right? And there's a name for this field. It's called the radial field. In the last class we discussed Kursi, and you'll notice that the spacing of the field lines here, right, they are increasing. So if you look at the spacing here, this is like that. And that is that, right? So what happens here is, there a second. what happens here is that the further you go, the spacing becomes more, right? And the greater the spacing, it represents a weaker field. So যে জিনিসটা নোটিস করা হয় that as you keep going further and further away, the field starts to get weaker, but it starts to get weaker exponentially. So if the strength here is 1, the strength here will be 1 by 4, and then 1 by 9, and 1 by 25 when it drops very rapidly. Okay, how do we know that? Through math, and that math is what we're going to learn eventually. Okay, so this is a representation of field around a mass here. This syllabus we deal with point masses. So point masses, you know, this is how it looks like. So this is the diagram. So you have to draw this diagram. This is the radial field. এটা হচ্ছে field around a point mass. Field around a point mass. Yeah, so the if your mass is here, for instance, right, it will experience greater force compared to when the mass is further away, and you can see evidences of that with objects in space. So when you're far away from Earth, the force that you experience is much lower compared to as you're getting closer and closer to the Earth. And the force is the greatest near the surface. You can't penetrate the surface of the Earth, so that's the maximum. But if there was a hole within the Earth and you kept going further in, right, the force would change accordingly. But yeah, our syllabus deals with outside the masses. So outside the mass, it's the greatest at the surface, and the further and further you go away, the force starts to weaken. Right, good question. Why are we not pulled to the core of the Earth? Heh, why isn't gravity just taking us into the core of the Earth? Very good question. Is there anyone who can answer that? Why aren't we squashed and taken into the center of the Earth due to gravity, right? The force of Earth. It's Earth after all pulling us. So হচ্ছে না কেন? Why aren't we moving into the Earth? Um, third law. Third law. Does it have to do with velocity of the Earth? Nah. Reaction, contact force. Yes, one is gravity is very weak. But then who opposes gravity to prevent it from happening? Yes, very good. So a couple of you figured it out. So the thing is, it is trying. The Earth is trying desperately to pull us into it, right? But the moment the object reaches the surface, there is another force that comes and plays a role here. And that force is called the contact force. It's the electrostatic repulsion from the electrons on the surface of the Earth. And that force is exponentially stronger than gravitational force, and hence gravity can win there. So it creates an equilibrium and it stops. So no matter how much you try, these electrons on the Earth's surface will push you out with that same force, preventing you from moving inwards. Because তোমাকে inwards যেতে হলে তো there has to be a resultant force, right? So সেটা হয় না. Now যেমন এই repulsionটা is not that strong in water. পানিতে এই repulsionটা অত strong না. So once you're in water, you actually move through the water and then eventually go to the bottom of the ocean, and there you stop again. So basically, the ground and its density and the materials have enough electrons in the surface to oppose you from moving inwards. Hence, you never go into the center of the Earth. Air, for example, can't stop you. That's why you fall through air. Right, so যে এটা ডায়াগ্রামটা আমি কিছু পয়েন্টস এখানে অ্যাড করতেছি, তোমরা ডায়াগ্রামটি কপি করে নিও। সো ফার্স্ট হচ্ছে arrows must point inwards since F is only attractive Right. Secondly হচ্ছে um, এটা তো অলরেডি মেনশন করছি বা আবার লিখে দিচ্ছি separation represents strength. They're inversely related. So more separation means less force or means lower strength. It'll eventually there are maths that will show us the reason in কেন এটা, but right now just diagram এর জন্য. And খুব important এই পার্টটা আমি কেমনে দেখে দাঁড়াও um here, paste yeah, so this is the fact that the angle here has to be 90 degrees to the surface. Okay, so এটা হচ্ছে lines must at leave perpendicularly to the surface. Right, so that's essentially it. The requirements for drawing your line. এটা ইউজ করে বাকিগুলো আমরা ড্র করবো। আমাদের সিলেবাসে we have 3 different lines or diagrams that you need to learn. So তিনটার মধ্যে this is the first one. This is the most basic one. But yeah. Which example? Could you repeat the example? কোন এক্সাম্পলটা? আচ্ছা, এখানে gravitational field is a region in which a mass experiences force. Field lines represent the strength of the field. The closer the lines, the stronger the field. The field lines will never intersect one another, and the arrows must always point towards the mass. This is because it's attractive in nature. হ্যাঁ, ওই জিনিসটা একটু just মনে রেখো, lines cannot cross each other. Uh, they must always enter a surface perpendicularly. Okay, so this is the field around a point mass. Let me know if you're done with the diagram. Okay, এখন হচ্ছে if you're done, খুব ইন্টারেস্টিং একটা জিনিস দেখবো. Uh, so pay attention what's happening here. So the thing is, if you're on the surface of the earth, right? Let's say right now, and this is the surface of the earth. We are here right now. And if you go further away from the surface of the earth, right, the strength of gravity doesn't change actually. Why? Because when you're on the surface of the earth, the value of G is 9.81. As you keep going further and further away, the value of gravitational field strength is still the same, right? So G is always 9.81. So G equals to 9.81 meter per second square. So problem হচ্ছে that's contradicting what we learned right now. Because what did we learn? We learned that the value of G or strength, right? Strength basically G বলা হয়, should decrease as you go further away. So as you keep going further and further away, right? It is supposed to get weaker. So the question is, why doesn't it? Because আমরা যখন হচ্ছে calculation করি, math করি, we see that the value of G is actually constant, but it does change, right? So can you tell me why is it that the value of G doesn't change for our math, like projectiles, or typically speaking, আমরা তো কোনো সময় এটা কনসিডারই করি না যে G ভ্যালু কমতে পারে, but isn't it what the diagram tells us? The further you go away, the G must get weaker, right? So why isn't it getting weaker? Why is it constant? কি মনে করো reason? Because we're inside the earth. No, আমরা তো earth inside না, আমরা earth উপরে. Not enough impact on the value of G, not enough distance. Yes, very close. So one of the reasons why the value of G isn't changing as much as anticipated is because the distances that we deal with, they're not really very large. I'll give you a context. It has অনেকের হচ্ছিল misunderstanding থাকে. G is actually the G that we deal with, right? We don't go very far from Earth, and most of the times হচ্ছে আমরা যে এইসব জিনিস নিয়ে কথা বলি, they're not really far away. Let's say satellites, okay? How far are satellites from the surface of the Earth? কেউ আমাকে বলতে পারবে? So if this is the Earth, right? A, B, typical satellites. Obviously, there are things that have gone beyond our solar system. Where do you think satellites would be in A, B, C, D তে? Satellites যে আমরা পাঠাই না in space, right? Where do you think satellites are? Is it A, B, C, D, or even like somewhere else, even closer or even further away? All right, so the correct answer is I'll give you guys the answer because তোমরা mostly A বলছো. The correct answer is not even A. It's actually that. I don't know if you can see that dot there. That is where we send satellites, right at the edge of our exosphere. Like, there's atmosphere, stratosphere, ionosphere, exosphere, right? We exosphere, which is only 100 kilometers up there. So the International Space Station, right, is only 100 kilometers above our head. মানে গাড়ি নিয়ে ট্রাভেল করলে couple of hours চলে যাবা. If your car goes straight up into the sky, right, you can reach International Space Station in few hours. It's very close. Rockets যে পাঠানো হয় to space to launch satellites or go to the International Space Station, it takes 21 minutes. Just, like that. দেখলে তো মনে হয় they're going on this, lifelong journey. Rocket উঠতেছে, যাচ্ছে, and probably, a few months later they'll reach there. It takes 21 minutes to enter space. যেটাকে official space বলা হয়. So, it's not really far away. So these distances are so close, right? And so small that the value of G doesn't really change there. Once you start to go here, there, and there, these places, right? Once you start to go to these places, the value of G becomes substantially different. So আমরা যেখানে থাকি, from the point of view of where we are, nothing really changes because the distances are really small. The radius of the Earth is 6,400 kilometers, right? So just 6,400 kilometers. এখানে আমরা স্যাটেলাইট সেন্ড করি 100 কিলোমিটার উপরে. That is a very small fraction of the entire size of the Earth, right? So it doesn't really make any difference to the calculations that we have. But then why is the value of G constant? So ওইটা হচ্ছে because constant যদি হয়, field lines must be what to each other? Can you remind me? If your gravitational field is constant, right, what must the field lines be to each other? No. Constant, Buchi, but what should the lines look like if the field is constant? Parallel. Yes, very good. They should look parallel, right? So how is it so? So এটা হচ্ছে because if you draw lines like this, and I'll just draw and show it to you. If you draw lines like that, I don't know if I can zoom in that much, but I'll try. If you draw lines like this, and if you go really close to the surface of the Earth, this is not even as close as I want to go, but I can allow for না. You'll start to notice these lines here, right? What do they look like? Are they diverging away from each other, or do they look parallel to each other? Yes, exactly. The spacing is so small that so to give you context, like Mount Everest হচ্ছে যেটুকু, that's Mount Everest. Okay, so the lines that you see here, they're almost parallel to each other. So আমি যদি এই যে yellow lines গুলো draw করি, and ধরো তোমাকে context না দিলাম, just yellow lines গুলো show করলাম, most people will probably say, yeah, they look kind of parallel, right? But they're not. Of course, they're not. They're actually diverging away. So at this level, they look parallel. That's why the value of G appears to be constant. But that's because you're looking at a very small region of the Earth's surface. As you start to go further and further away, these will start to become more prominently spread out. And that's when it becomes obvious that G is changing. Exactly. So the Earth's surface appears flat. It is not flat. It appears flat, right? And because the Earth's surface appears flat from our point of view, the lines that leave the surface appear parallel from our point of view because we are within the 5-degree angle of approximation. I think we talked about this, remember? That if it's less than 5 degrees, things behave differently. So if you're within a very small angle of the Earth's surface, right, the surface will look flat to you, but it is actually a part of a curvature. And if the surface appears flat to you, lines will appear parallel to you. The further away it is, the smaller the value it is. Correct. So as you start to go further and further away, like here, for instance, it is quite spread out. So the strength is weaker here. And even more further away, even weaker there. So eventually it gets weaker and weaker as further and further you go. So AJ, why is gravitational field near the surface of the Earth constant? It's because near the surface of the Earth, the lines emerge parallel to each other, and these parallel lines result in a uniform field. As the lines move further out, the separation becomes more pronounced, and the strength no longer remains constant. Okay, so it appears to be constant near the surface of the Earth, which was what we had till AS. AS পর্যন্ত আমরা Earth's surface কাছেই থাকতাম. G is always 9.81. Starting from next class onwards, G is not going to stay 9.81 because we'll go further, deeper out into space. And that's where the value of G will start to get like very different. And how different, that we'll learn how to find out. So, if you're a million kilometers away from the Earth, right, what's the value of G? We need to figure that out. So that's where Newton's law of gravitation comes into play. Anyways, this is gravitational field. And ফিল্ডেরটা মোটামুটি হয়ে গেছে। আমরা হচ্ছে নেক্সট ক্লাসে হচ্ছে couple of more diagrams করব না, diagrams গুলো অ্যাকচুয়ালি পরে করব। আমি নেক্সট ক্লাসে হচ্ছে I'll start with the Newton's law of gravitation. খুবই ইম্পর্টেন্ট পার্ট। এটা যদি পারো then you'll find the rest of the chapter very manageable. Like I would say 80% of it খুবই straightforward. এই just potential part একটু challenging. This math here. It's only a math. So ওইটা is the only challenge in this chapter. Anyways, সার্কুলার মোশনটা ওভার। তোমাদের কিন্তু সার্কুলার মোশনের টেস্ট হবে। তোমাদের ফার্স্ট টেস্ট হচ্ছে হওয়ার কথা ছিল কালকে অ্যাকচুয়ালি, বাট since I can't take physical classes, so once we reopen you'll have a test on circular motion, so keep preparing for it, and meanwhile we'll be doing gravitational fields.